Hello, welcome to our channel. Today we'll be discussing polarization. It's the last part of phase, and starting off, we'll be seeing how the phenomenon of polarization works. So I've drawn this diagram for you, and it's of a light and the particles orientation. So I've taken an example of a bulb. Okay, a very common light source present in everyone's room. We have a bulb. Now the light that is coming off from bulb, it's unpolarized. So this diagram basically represents an unpolarized light. Unpolarized light, the particles in it are moving in all directions. They do not have an orientation, right? However, a polarized light is an orientated one. It's not random. It's in a particular specified manner. Like for instance, let's suppose I take a polarized light which is only moving in vertical direction. So all the particles are moving in vertical direction, right? Or let's suppose we take this diagonal. So all the particles are moving in diagonal direction. There isn't any particle moving in vertical direction or in horizontal, no. All the particles are moving in a specified similar direction. They all are orientated in the same manner, and that's an example of a polarized light. So we can achieve polarization using a filter, which is also known as a polarizer or an analyzer. So we have two types of filter, a polarizer and an analyzer. Now coming on to and also one other point worth mentioning is that polarization is a phenomenon that is only associated with transverse wave. Longitudinal waves like sound waves, they do not exhibit polarization. So if a MCQ comes in that what is one phenomena that is only exhibited by transverse waves, or one phenomena that differentiates transverse and longitudinal waves, so you will tick on the answer that states polarization. So polarization, option number, now we have covered 1. We'll be coming on to 2. Now 2 states that recall and use Malice's law to calculate the density of a plane, polarized electromagnetic wave. So Malice's law is, as mentioned over here, it's I equals to, I'm gonna rub it to have some space. Malice's law is I equals to I naught cos square theta. Now this I naught represents the original intensity, like the intensity of the unpolarized light, and this represents the intensity that will be coming off after the light has passed the polarizer. So this is the intensity we'll be calculating in a few minutes. I'll show you how to calculate the intensities. Another thing is that now you can manipulate this formula if you are asked to use Malice's law in terms of amplitude. So you can manipulate it in a way that we know that I is proportional to a square, amplitude square. So I can be replaced with amplitude square, and the formula would look like something like this. So if you have your values in terms of amplitude and not intensity, you can use this equation as well to do the calculations. So to help you understand how we will use the formula, I've drawn this diagram. It's a question that I have designed, and we'll be looking on how to go about it. So first off, starting with the unpolarized light. This is an unpolarized light, right? Because it's unorientated. And this is a polarizer. This is what a polarizer looks like. Now this, if you look closely over here, this vertical line represents that whatever light passes through will come out as vertically orientated. Now if it had been like something like this, now this is orientated in horizontal plane. So all the light that would be coming off from it would be in this particular direction. In this case, the light would look like in this direction, right? So now we are told that, for instance, the unpolarized light has an intensity. Where's my, okay, let's use this color. The unpolarized light has original intensity of, let's suppose, 60. Say 16 watt per meter square. Now it passes through this polarizer, and what will be the intensity? Now, a point worth mentioning over here is that the orientation of this polarizer doesn't matter. If you, whatever unpolarized light that passes through the first polarizer will have intensity half the original. So for instance, if I had a polarizer that was orientated in this direction, in a diagonal direction, right? Like for instance, I had unpolarized light. Say we shown it on a polarizer that was oriented in this direction, like something diagonally along the z-plane. So the light would have an intensity half the original. So this is a point that you need to know, like you need to have this in the back of your head. Now the intensity of this light is 8, which is the half of 16, 8 watt per meter square. Now comes the part of understanding where you need to listen carefully to know that how the formula works. I mentioned Malthus's formula. It was I equals to I naught cos square theta. Now what this theta is? Theta can have two definitions. One definition of theta, let's use gray. Theta could be the angle between polarizer and analyzer, or theta could also be the angle between light ray that is coming towards the polarizer and the transmission axis of that polarizer. Now what an analyzer is? The first polarizer is obviously called a polarizer. The second one, we can also call it polarizer number 2 or an analyzer. So in this particular case, this one is our analyzer. Theta says that it's the angle between the polarizer and the analyzer. So using the first definition, our theta would be, because this is oriented in the vertical plane, so I've drawn this vertical plane over here, the vertical line, and this polarizer has been tilted to 30 degrees towards, it has been tilted basically 30 degrees clockwise. So the angle between the polarizer and the analyzer is 30 degrees. So the formula goes by that let's use another color, pink, okay. I equals to I naught cos square theta. Now this I naught is the intensity of the light that is coming towards this polarizer. So this would be 8, not 16, okay, mind you. So 8 into cos theta 30, and we write square. So cos 30 is under root 3 over 2. Let me just check. Yeah, under 3 over 2. So under root 3 over 2 square, so that's 8 into 3 over 4, so that's 6. 6 is the intensity of the light that is coming from the analyzer, right? This light over here has an intensity of 6. Now we move on to another polarizer because our objective told us to basically recall and use Malthus's law for a series of polarizing filters as well. If you look closely over here, that's what I'm doing over here. I'm showing you how to use the formula for a series of polarizer. So I naught for this particular polarizer or analyzer is, I'm using purple for this calculation only. I naught is 6, and we need to calculate the intensity of the light that is coming from this polarizer. So it's I naught cos square theta. Now what is the theta over here? Theta, as I mentioned in my definition of angle, theta is the angle between light and transmission axis of that polarizer. So light in this, the light that was coming off from this polarizer was orientated with respect to the blue light that I've drawn over here, because that was the transmission axis. So the light that would come off from this polarizer would obviously be in that direction. So this is the direction of light, this blue one, direction of light, and yellow one is the transmission axis of this polarizer number 3. I'm assuming, yes, polarizer number 3 has the transmission axis represented by the yellow line. So the angle between the direction of light that came off from the polarizer number 2 and the transmission axis polarizer number 3 has an angle of 10 degrees between them. So a theta in this case is, whoops, where did it go? Okay, here it is. Theta would be in this case 10. So I naught is 6 cos 10 square. So you can just use calculator for this calculation because I don't know the exact value of cos 10. So we have 6. This is giving me a value of 5.82. So the intensity, final intensity of the light coming off from the polarizer number 3 is 5.82. So our intensity of light, as you saw, gradually decreased from 16 to 8 to 6 and then to 5.82. So we can use polarizer as well to decrease the intensity gradually. So that's all for this particular section. Thank you for watching.